Hello everyone, my name is Nely Montelongo and this is my course project. Okay, so I am dividing my statements into two components for this project. So first we're going to discuss the existence of quadratic residues modulo the power of n odd prime. And then second, we are going to show that A is a quadratic residue modulo the kth power of a prime P if and only if it is a quadratic residue modulo P itself. So again, first we're going to discuss the existence of quadratic residues modulo the power of an odd prime. So right here, what is a quadratic residue? A quadratic residue is, we can explain it as let A and n be integers and with n being bigger than 0. So it would be a natural number, and the greatest common divisor of A and n is 1, so the coprime. Then A is set to be a quadratic residue modulo n if x is squared, then it would be congruent to A mod n if it's solvable. So the key word here, if it's solvable, then it is a quadratic residue. So right here, what is a non-quadratic residue? If it is a non-quadratic residue, it is non-solvable. Okay, so it would not be able to have a solution. Okay, so for example number 1, if we have n is equal to 7, I am first going to write it down and then I can go ahead and explain it. So as we see here, we are putting all of our inputs and our outputs and what they are congruent to. And all of them to mod 7. So is equal. Oops. Okay, perfect. So if we see, we have the example of n is equal to 7, which would prove a result because 7 is an odd number. And remember that odd numbers are numbers that cannot be divided exactly into pairs. So we are going to square all of the numbers as we saw here, and it would be mod 7. Okay, so and then we see the outputs. So if we take 1 squared congruent to 1 mod 7, and then we have 2 squared congruent to 4 mod 7, then we have 3 squared, which is equal to 9, which would then be congruent to 2 mod 7. 4 squared equals 16, congruent to 2 mod 7. 5 squared equals 25, congruent to 4 mod 7. And 6 squared is equal to 36, congruent to 1 mod 7. So the structure here that we see, if we fold it exactly at this line, so I can put that if we are folding it exactly right here, between 3 squared and 4 squared, it would show us that they are matching. So we have 2, 2, 4, 4, and 1, 1. Okay, meaning that those would be part of the results that we can later prove. Okay, so now we want to list the quadratic residues based on what we just saw. So first we can say that we see that 1, 2, and 4 are quadratic residues to so quadratic residues to mod 7. Okay, so 1, 2, and 4, would be quadratic residues to mod 7. And then the non-residues would be the ones that we have remaining. So that would be 3, 5, and 6 that are quadratic non-residues. So again, our list for quadratic non-residues would be 3, 5, and 6. Okay. So now we are going to move on to statement number 2, which is to show that A is a quadratic residue modulo the kth power of a prime P if and only if it is a quadratic residue modulo P itself. Okay, so first we can define a prime number as a whole number that has only two factors, 1 and itself. For example, so my example here would be if I have 3, we see that 3 is a prime number because we can only have 1 and itself. So these two right here would be our factors. Okay, so for example number 2, we have x is an integer such that x squared is congruent to x mod p to the k power, then x is congruent to 0 or 1 mod p to the k power. So we see that we have x squared is congruent to x mod p to the power of k. Then we have x squared minus x is equal to p to the power of k times n. Since the highest common factor of x minus 1 to x is equal to 1, and either p over x or p over x minus 1, because x minus 1 is equal to p to the power of k times n. And lastly, suppose that we have p over x, then p does not divide x minus 1, since the highest common factor of x minus 1 to x is equal to 1, then x over p times x minus 1 is equal to p to the power of k minus 1 times n, as we see right here at the very bottom. Okay. Which implies that p to the power of k minus 1 divides over p, because the highest common factor of x minus 1 to the power of k minus 1 is equal to 1. Since p does not divide by x minus 1, we can see that x is divisible by p to the power of k. Okay. If x is congruent to 0 mod p to the power of k, we can suppose that p divisible by x minus 1, then p does not divide x, since the highest common factor of x minus 1 to x is equal to 1, then we see that x minus 1 over p times x is equal to p to the power of k minus 1 times n. So this right here, which also implies that p to the power of k minus 1 divides x minus 1. So this section right here. Minus 1 divided by p, because the highest common factor, x to p to the power of k minus 1, since p does not divide by x, we can see that x minus 1 is divisible by p to the power of k, then x is congruent to 1 mod p to the power of k. So we see that x squared is congruent to x mod p to the power of k. And then we see that x is congruent to 0, or it would be 1 mod p to the power of k. So that is it for my presentation, and here are my references. Thank you so much.